Limiters are confusing, but I think once you kind of get the trick of it, the hang of them, actually you're well on the way to really understanding what's going on with a diode anyway, so I think they're important. So we might have this circuit here. Oops, I need a diode in that circuit. We might have this circuit without a diode. We need to put in a diode. Just squeeze it in there. All right, now it's a limiter circuit. And this diode serves to prevent the output from going crazy. Now, I'm going to stop drawing them quite with so much detail for you, but you should recognize and you should be comfortable with this circuit would be exactly the same if I drew it like this. Or the output results of this circuit would be the same. We had 3.2 volts there. V out here and V in. This is identical to this circuit. All I did was switch the location of the diode and the source, the battery. And once I've drawn it like that, then hopefully you would be comfortable with me drawing it like this, where we've got V in, we've got a resistor. We don't really care the size of that resistor. We've got 3.2 volts. No, I should draw it the other way. Let me put that up the other way. So we've got 3.2 volts on that resistor, or that diode. So really, the diode is the square end of this triangle here is touching the output line here. So, or the flat end, I should say. So really, we've got a circuit that looks like this. I didn't draw my diode very nicely. Just fix that. Still not a great diode, but anyway, that's how I might often draw it. That this is more like how you would actually see it in a data sheet or a instruction set of some kind, and it doesn't matter which of these three that we're analyzing; they're all equivalent. And so the way I will understand what's going on is if we think about it with the input voltage at minus infinity, if we have a super negative input voltage, if this is negative infinite volts, right, then we have a very negative voltage here that's kind of basically overpowering this battery here, and the diode will be off. And that makes it easy to draw the transfer characteristic in that situation. So if the diode's off, it doesn't exist, and the output just equals the input. And remember, we've got this dotted line on the transfer characteristic V out versus V in, and we must be on that. And at minus infinite voltage on the input, then output equals input. Because with the diode off, it turned into just this circuit here. VI feeding a resistor, feeding V out. The diode's an open circuit if the diode's off, and V out is just exactly equal to V in. Now, the other case is with Vi is equal to infinity, positive infinity. In that case, we have an extremely positive voltage here. We have plus infinity here. The massive voltage here will overpower the supply again, and we'll have a very strong voltage here. The diode will be turned on. If the diode's turned on, then it's a short circuit. So now we'll have the diodes on, and we have VI, a resistor with a short circuit to 3.2 volts. Well, I should draw that going up, shouldn't I? Because that's how I drew it over there. Positive voltage. So we've got VI. Diode is a short circuit, and the output should be equal to 3.2 volts. And so if we did the transfer characteristic for that, we've still got this dotted line. We know that this is positive, or that's equal. And here we have the output is 3.2 volts. Fixed for a positive infinite. And so if we just draw these lines together, look at that, and overall the characteristic, transfer characteristic V out versus V in will look like this. Output equals input in this region here. Anytime the input is less than 3.2 volts, the value on the supply here, anytime the input's less than 3.2, the diode is turned off, and output equals input. If the input is larger than 3.2, then the power supply here, this battery, limits the output voltage to 3.2 volts. And that's why we call it a limiter. If we add another page here and do some of the other possibilities. So we could have a resistor with the diode facing into the output, minus 5 volts there. V out, R, again, it really doesn't matter what size the resistor is. With V in equal to minus infinity, if we have a very strong negative voltage, a negative infinity here, then this diode should be turned on because we have plus and minus. Even though we've got minus 5 volts here, we're even stronger negative voltage here, and the diode will be turned on. It will be a short. And if it's on, that means that we must be limited by this minus 5 volts. The short, when this turns to a short, means that this minus 5 volts will appear on the output too. And so we've got, let's see, we've got a dotted line through here. And for negative infinity, we are at minus 5 volts. All right. The other case is for a positive infinite voltage input. VI is equal to positive infinity. Then the diode's off. It's got to be, it's the opposite of being on, right? So for a very large input voltage, for plus infinity here, we have a larger voltage here than here, the diode's off. That's what that means. So with the diode off, we're in that region where output equals input. We have just a circuit. I have just V out and V in. The diode is gone. It's an open circuit. And for a positive infinite, we got something that looks like that. So if we combine these two, V out and V in, we've got this characteristic here. We know for a very positive voltage, it's It's right on that line. That's this one. And we know for negative input voltage, we're at negative 5 volts. So it'll be limiting it right there. For any input greater than 5 volts, greater than negative 5 volts, the output will equal the input. But for any input voltage less than 5 volts, it just stays at 5 volts. It won't get any worse than that. Circuits like this are really useful in all kinds of important places. So another one. That's too many squiggles on that line. Sometimes it just doesn't want to draw. I don't know why. Let's say we have +6. V in, R, and V out. So have the transfer characteristic V out in V in, and we have the dotted line for V in is equal to negative infinity. For a very negative voltage here, negative infinity there, the diode will be on. When the diode is on, we are limited to this voltage here. It's a short circuit to that, so it's going to be 6 volts for negative infinity. It's a positive 6 volts. And for a positive infinity, the diode must be off. For a very large positive voltage, infinite, we have a greater voltage here than here. The diode's turned off, and it's an open circuit. In that case, output is equal to input. And we can just draw the intersection. And if you're being extra careful, you erase, oops, the wrong lines. Add a little bit of a line there. V out equals Vn. And those numbers here, we've got 6 volts, and this occurs at +6 volts. If we had a circuit that looked like this, if we have Vn, little resistor, and say we went to +4 volts, plus psi, so +4 volts, and we have another diode. It's basically facing the same way, but down here at -4 volts, and V out, you should be able to quickly convince yourself that we have a transfer characteristic, V out and V in, that is V out is equal to V in over a certain range. Above and beyond that, at -4 volts and +4 volts, will be limited. Oh, I can't draw 4s today. Gotta turn this iPad sideways. This would be useful if there's some kind of input protection device or input system that prevents an input value from going too large and damaging the circuit. It will never go beyond 4 volts. But if the the amplitude of the the size of the input voltage is less than 4 volts, the input will be just translated on to the output of this circuit, which might actually be the input of the whole, the rest of the circuit, whatever we have there. Shouldn't just draw an op amp, but whatever the rest of the circuit is, this kind of arrangement of diodes will limit the incoming voltage and help prevent damage.